Hello, science enthusiasts. Welcome back to Science and Amp Technology, the channel where we explore the wonders of the universe. Today, we're embarking on an intriguing journey, one that has captivated the minds of thinkers, dreamers, and scientists for ages. We're delving into the captivating world of time travel, exploring its physics, its paradoxes, and its possibilities. So hold on to your seats, or should we say, your time machines. Because we're about to take a journey through the very fabric of time itself. Before we dive into time travel, we first need to understand what time is. Now, you might think it's as simple as the ticking of a clock, but there's a lot more to it. Time, in fact, is a dimension. Just as we move through space, we also move through time. Picture time as a river, continuously flowing, carrying everything in its current. We're all on this river, flowing from the past, through the present, and into the future. And just like a river is part of the Earth's landscape, time is part of the universe's fabric. It's woven together with space, forming a four-dimensional tapestry known as space-time. This is our cosmic stage where we perform the dance of existence, moving not just in 3 dimensions of space, but also in the 4th dimension of time. So, remember, time is not just a simple ticking clock. It's a dimension, much like space, and it's intimately connected to the fabric of the universe. To explore time travel, we need to delve into Einstein's theory of special relativity. This theory, introduced by Albert Einstein in the early 20th century, revolutionized our understanding of space and time. It tells us that the laws of physics are the same for all non-accelerating observers, and the speed of light within a vacuum is the same no matter the speed at which an observer travels. But the most intriguing part of special relativity is the concept of time dilation. It suggests that time can stretch and squeeze depending on your speed and gravity. So, if you were to travel at near light speed, time would actually slow down for you compared to someone stationary. You'd age slower. It's a mind-bending concept that challenges our everyday experience of time as a constant, unchanging entity. This understanding of time as a flexible, relative construct is at the heart of any discussion on time travel. It's a fundamental concept for understanding time travel. Ever heard of the famous twin paradox? It's a thought experiment that demonstrates the effects of time dilation, a key concept in Einstein's theory of special relativity. Imagine a pair of identical twins. One remains on Earth, while the other embarks on a journey into space at nearly the speed of light. According to special relativity, the moving twin would experience time more slowly than their sibling back on Earth. This is because the faster you move through space, the slower you move through time. It's a bit like a cosmic speed limit. So when the space-traveling twin returns, they would be younger than their Earthbound sibling. Now, this might sound like something out of a science fiction novel, but it's a fundamental aspect of our universe. Time isn't the same for everyone. It's relative to your speed and gravity. This real-world example perfectly illustrates how time dilation works. Wormholes, the stuff of science fiction, right? Well, not quite. They're actually a fascinating theoretical concept born out of Einstein's general relativity. A wormhole, in essence, is a bridge or tunnel that connects 2 different points in space-time. Imagine folding a flat piece of paper, the universe, in half, then poking a hole through it. That hole or shortcut is what we call a wormhole. So, how does this tie into time travel? Well, if wormholes exist, and if we could somehow manage to keep them stable, they could potentially function as a portal through time. This is because the 2 ends of a wormhole could theoretically exist in different times. One could be in the present, the other in the past or future. However, it's crucial to note that this is all purely theoretical. We have yet to observe a wormhole in nature, and there are significant hurdles to overcome. For one, wormholes are thought to be incredibly unstable, collapsing instantaneously without some form of exotic matter to keep them open. Additionally, even if we could ensure a wormhole's stability, safely traversing it presents another set of challenges. Despite these hurdles, the concept of wormholes and their potential role in time travel continue to captivate scientists and science enthusiasts alike. The study of wormholes pushes the boundaries of our understanding, encouraging us to question, explore, and dream. These hypothetical shortcuts through space-time might be the key to time travel. The grandfather paradox, a classic time travel conundrum. Imagine this. You've got a time machine, and you decide to take a trip back in time to meet your young grandfather. But what would happen if you were to prevent your grandfather from meeting your grandmother? Would you instantly vanish as your very existence is now an impossibility? Or would you continue to exist, creating a paradox that defies the laws of cause and effect? This scenario is what's known as the grandfather paradox, It's a thought experiment that plays with the notion of causality, where an action's effect happens before its cause. It's a concept that seems to fly in the face of our day-to-day experiences, where cause and effect follow a strict order. This paradox raises some fascinating questions about the nature of time and existence. It challenges our understanding of reality and forces us to question the fundamental rules that govern our universe. Time machines have been a staple of science fiction, but could we ever build one in reality? This is the question that teases the minds of many physicists and science enthusiasts alike. As we dive into the world of theoretical physics, we encounter several intriguing concepts. One of them is rotating black holes. Unlike stationary black holes, these cosmic entities possess a property known as frame dragging, where they pull the surrounding space-time along with their rotation. Theoretically, if a spaceship could survive the journey into a rotating black hole, it might be possible to emerge in a different time, or perhaps even a different universe. Another fascinating concept is the Tipler cylinder. Named after American physicist Frank Tipler, it's a massive and infinitely long cylinder that's spinning at a high speed. According to Tipler's calculations, a spaceship flying around the cylinder in a spiral path could find itself in a closed, time-like curve, a loop in space-time that returns to the past. However, these concepts come with their own set of challenges. For instance, the Tipler cylinder requires an infinite amount of energy, and the journey through a rotating black hole is likely to be a one-way trip. Despite these hurdles, the concept of time machines sparks our imagination and pushes the boundaries of what might be possible. It's a testament to the human spirit's unending quest to understand and potentially master the fundamental forces that govern our universe. We've covered a lot, and there's much more to explore. Let's dive deeper into the rabbit hole that is the physics of time travel. Consider closed, time-like curves, a concept that comes to us from the world of relativity. These curves, existing in four-dimensional spacetime, theoretically allow an object to return to its own past. Imagine looping back on your timeline, like retracing your steps in a cosmic walk. Now let's venture into the realm of cosmic strings, hypothetical one-dimensional defects in the fabric of the universe. Born out of the Big Bang, these strings, if they exist, might be thinner than an atom yet incredibly dense. Just passing by one could warp space-time enough to create a path to the past. However, these ideas, while fascinating, are highly speculative and face numerous scientific challenges. Nevertheless, they illustrate the sheer breadth and depth of theoretical physics. The theoretical possibilities for time travel are mind-boggling. As we conclude our journey through the physics of time travel, we can't ignore the ethical questions it raises. Time travel isn't just about the thrill of the journey, it's also about the potential consequences. Would it be morally right to change the past, even if it meant improving the present? What if our actions inadvertently set off a chain of disastrous events? These ethical dilemmas add another layer of complexity to the concept of time travel. If time travel were possible, how would we handle the consequences of altering the past? There you have it, folks, the physics of time travel. We've journeyed through the dimension of time, explored Einstein's theory of special relativity, and unraveled the mystery of the twin paradox. We've ventured into the realm of wormholes, grappled with the grandfather paradox, and considered the feasibility of time machines. We've pondered the theoretical possibilities, from closed time-like curves to cosmic strings, and confronted the ethical dilemmas that time travel could bring. Though the concept of time travel has captivated our imaginations for centuries, it remains just that, a concept. It's an intriguing theory, rich with possibilities and fraught with paradoxes. The reality of time travel, if it ever comes to pass, may be far different from what we've imagined. Thank you for joining us today on Science and Amp Technology. We hope you've enjoyed this journey through the physics of time travel. Until next time, keep exploring the cosmos.
For more updates, subscribe to our channel, click the show links and enjoy watching the videos.